Okay, hi guys. So in this lecture we'll be talking about skew conformers. So conformers accept 0 and 180 degree. So any angle between the two specified groups are called skew conformers, right? So skew conformers are skew conformers. So isomers having any angle except 0 and 180 degree between two specified groups are called skew conformers. Okay, and example of skew conformers can be gauche and partially eclipsed. Okay, so as you know, the gauche and the partially eclipsed are not means the specified groups are not at 0 degree or 180 degree. They are somewhere in between at 60 and 120 degree, hence they are gauche and partially eclipsed. So now next we will see a graph of the potential energy of different conformers and with dihedral angle. On x-axis and potential energy on y-axis. Okay, so we have angles such as 0 degree, 60 degree, 120 degree, 180 degree, 240 degree, 300 degree and 360 degree. Okay, so the potential energy at 0 degree, when the dihedral angle is 0 degree between the two CH3 in case of butane, between the second carbon and third carbon atom, the rotation was considered, same bond rotation between second carbon and third carbon was considered. So in that case you can say that the potential energy was, for 0 degree it was the highest, or it was called fully eclipsed, and at 60 degree it was called gauche. It was called partially eclipsed at 120 degree. Let me redraw it again. At 180 degree it was known as 180 degree it was called staggered, so it had the least potential energy. At 240 degree it was again called partially eclipsed. At 360 degree it was at 300 degree it was called again gauche. At 300 degree it was called again gauche, and at 360 again it was fully eclipsed. So this is how the trend goes on. So at 0 degree it was called fully eclipsed, at 60 degree it was called gauche, at 120 degree it was called partially eclipsed, at 180 it was staggered, at 240 again it was partially eclipsed, at 300 it was gauche, and at 360 again it was fully eclipsed. Okay, so this is the potential energy of different conformers. So let me define what is the dihedral angle, the term I am using here. Dihedral angle. So angle between two specified groups in Newman projection is known as dihedral angle. So it is nothing but angle between two specified groups in Newman projection is called dihedral angle. Okay, and what are skew conformers? Again, by the definition, all conformers which is found in between eclipse and staggered form is known as skew conformers. So another way of putting the definition of skew conformers is all the conformers which is formed or which are formed in between eclipsed and staggered form is known as skew conformers. Okay, so what is a rotational barrier? Let me define what is a rotational barrier before going on further with the term. Okay, so rotational barrier is nothing but energy difference between the most stable conformer and the least stable conformer is the rotational barrier. Energy difference between the most stable and the least stable conformer is called rotational barrier. Okay, so let us draw some of the most stable conformers of the following compounds. So let's take some examples wherein you have to draw most stable conformers of the following. Okay, so first example is you have to draw the most stable conformer of an hexane between C2 and C3, or in other words between carbon 2 and carbon 3 the rotation would be there. Okay, so let us look at carbon 2. So this is the second carbon. So the most stable conformer, as you can guess, would be, yes, staggered. So in which the two bulky groups would be at 180 degree to each other. So CS3, and for the second carbon we would have H, not exactly staggered, but yeah, means for the staggered, actually in the previous definition I meant for the two similar groups, but here we will have CS3 at the second carbon, and at the third carbon we will have CS2 and CS3. So this form is also staggered only. Staggered need not be only for the similar groups, as you might be thinking that it is a CS3 group and it is a propyl group. It is still a staggered because the most bulky groups are at the 180 degree position. It is not that the two atoms or the groups should be identical, but the most bulky groups should be at 180 degree, which is there in this compound. Okay, so let us take a look at the second example where we have propane, and obviously between the second and third only. So you can put second, this is first carbon, this is the second carbon, and the ring is the third carbon. So you can put any H anywhere. Okay, third example is you have to do it for 2,3 dimethyl butane. So for 2,3 dimethyl butane we have something like this is the structure for 2,3 dimethyl butane. And this. Okay, so and you have to rotate across this bond. So the most stable would be, this is the first carbon atom, you have H here, you have two CS3s attached to this carbon atom. Okay, then on this carbon atom this would be a ring. Okay, and two CS3 have to attach. So how to place the rest of the CS3s? It should be, this is 180 degree for this one, and this should be 180 degree for this one, and the remaining H. So this would be the most stable. Okay, now let us check for this. So we have this compound and you have to take this bond into rotational consideration. Okay, so what would be the structure? So let's suppose I start from this carbon. You can start from any carbon, both are identical only. So this is H, this is H, and we have a OH here. This is the second carbon. On the second carbon I have to attach one OH and two H. So where should I place? I would be placing OH not here but here rather. Why? Because I can see that a hydrogen bonding can occur between the oxygen atom and the hydrogen of this OH and the oxygen and hydrogen of this OH. Okay, so for the same reason I am attaching OH here and the rest of the hydrogen here. Okay, so you have to, this is an important example because we went slightly off track to accommodate the possibility of hydrogen bonding as well, which is intramolecular hydrogen bonding. I hope we have discussed about it and you have remembered the same from our past lectures because of intramolecular hydrogen bonding. Okay, now let us have a look at this. So what would be the case for this compound? So for this compound, let's say I am using this as my first carbon. So OH is attached here, H is here, H is here. We come to the second carbon, and to the second carbon again I will attach F here. Why? Because intramolecular hydrogen bonding can happen between H and F atoms. Okay, and again I have fulfilled the remaining hydrogen valencies. Okay, so we'll look into more of the structures and we'll look into an important concept called Gaussian effect in the next lecture. So till then, good luck and goodbye.